So here's a quiz. Let's assume we fit all the 23 parameters of the Bayes network as explained using maximum likelihood. Let's now do classification and see what class a message ends up with. Let me start with a very simple message, and it only contains a single word just to make it a little bit simpler. What's the probability that we classify this one-word message as spam? And the answer is 0.1667 or 318. How do I get there? Well, let's apply Bayes' rule. This form is easily transformed into this expression over here. Probability of the message given spam times the probability of spam over the normalizer over here. Now we know that the word sports occurs 1 in our 9 words of spam. Now prior probability for spam is 3/8, which gives us this expression over here. We now have to add the same probabilities for the class ham. Sports occurs 5 times out of 15 in the ham class, and the prior probability for ham is 5/8, which gives us 3/72 divided by 18/72, which is 318 or 1/6. Let's do a more complicated quiz. Say the message now contains 3 words. Secret is secret. Not a particularly meaningful email, but the frequent occurrence of secret seems to suggest it might be spam. So what's the probability you're gonna judge this to be spam? And the answer is surprisingly high. It's 25/26 or 0.9615. To see, we apply Bayes' rule, which multiplies the prior for spamness with the conditional probability of each word given spam. Secret carries a third, is a 9, and secret a third again. We normalize this by the same expression plus the probability for the non-spam case. 5/8 is a prior, secret is 1/15, is 1/15, and secret again. This resolves to 1/216 over this expression plus 1/5400, and when you work it all out, it's 25/26. A final quiz. Let's assume our message is today is secret. And again, it might look like spam because the word secret occurs. I'd like you to compute for me the probability of spam given this message. And surprisingly, the probability for this message to be spam is 0. It's not 0.001, it's flat 0. In other words, it's impossible, according to our model, that this text could be a spam message. Why is this? When we apply the same rule as before, we get the prior for spamness, which is 3/8, and we multiply the conditional for each word into this. For secret, we know it to be a third, for is to be a 9, but for today, it's 0. It's 0 because the maximum likely estimate for the probability of today in spam is 0. Today just never occurred in a spam message so far. Now this 0 is troublesome because as we compute the outcome, and I'm plugging in all the numbers as before, none of the words matter anymore. Just the 0 matters. So we get 0 over something, which is plain 0. Are we overfitting? You betcha. We are clearly overfitting. It can't be that a single word determines the entire outcome of our analysis. The reason is that our model to assign a probability of 0 for the word today to be in the class of spam is just too aggressive. So let's change this. One technique to deal with the overfitting problem is called Laplace smoothing. In maximum likelihood estimation, we assign to a desired probability the quotient of the count of the specific event over all events in our data set. So for example, for the prior probability, we found that 3 over 8 messages are spam. Therefore, our maximum likely estimate for the prior probability of spam was 3 over 8. In Laplace smoothing, we use a different estimate. We add a value k to the count and normalize as if we added k to every single class that we're trying to estimate something over. This is equivalent to assuming we have a couple of fake training examples where we add k to each observation count. Now if k equals 0, we get our maximum likely estimator. But if k is larger than 0 and n is finite, we get different answers. Let's set k equals 1. And let's assume we get one message and that message is spam. So I'm going to write it one message, one spam. What is P of spam for the Laplace smoother with k equals 1? Let's do the same with 10 messages. And we get 6 spam and 100 messages, of which 60 are spam. Please enter your numbers into the boxes over here. The answer here is 2 over 3, or 0.667. And it's computed as follows. We have one message, which one is spam. We're going to add k equals 1. We're going to add k equals 2 over here, because there's two different classes. So k equals 1 times 2 equals 2, which gives us 2/3. The answer over here is 7/12. Again, we have 6 over 10, but we add 2 down here and 1 over here, so we get 7 over 12. And correspondingly, we get 61 over 102. It's 60 plus 1 over 100 plus 2. If we look at the numbers over here, we get 0.5833 and 0.5986. Interestingly, the maximum likelihood in the last two cases over here would give us 8.6, but we only get a value that's closer to 0.5, which is the effect of our smoothing prior to the Laplacian smoothing. Let's use the Laplacian smoother with k equals 1 to calculate a few interesting probabilities, P of spam, P of ham, and then the probability of the words today, given that's in the spam class or the ham class, and you might assume that our vocabulary size is about 12 different words here. This one is easy to calculate for spam and ham. For spam, it's 2/5, and the reason is we had previously 3 out of 8 messages assigned to spam, but thanks to the Laplacian smoother, we add 1 over here, and there's 2 classes, so we add 2 times 1 over here, which is us 4 over 10, which is 2/5. Similarly, we get 3/5 over here. Now the tricky part comes up over here. Before we had 0 occurrences of the word today in the spam class, and we had 9 data points. But now we're going to add 1 for Laplacian smoother, and down here we're going to add 12. And the reason why we add 12 is because there's 12 different words in our dictionary. Hence, for each word in the dictionary, we're going to add 1. So we add a total of 12, which gives us a 12 over here. That makes 1 over 21. In the ham class, we had 2 occurrences of the word today, over here and over here. We add 1, normalized by 15, plus 12 for the dictionary size, which is 3 over 27, or 1/9. This was not an easy question.